Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering, and we'll extend our discussion on thermal properties of materials. So in this video we are going to discuss about two important concepts. This is the first one. This is absolute zero temperature. Okay, like I said, we are discussing the thermal properties of materials. So right from the beginning, when we started our discussion related to thermal properties, I told you that every discussion that we'll have on thermal properties, it will have in one way or the other temperature or heat. These two things will be involved. Now we discussed that heat and temperature, they are like interrelated. Okay, so this is the concept of absolute zero temperature, the minimum possible temperature which is taken into consideration for thermodynamic analysis. Now we have already discussed that there are three important thermodynamic parameters which come into play in any discussion related to thermal properties of materials: pressure, temperature and volume. Okay, and the various interrelationships that they have, they are quantified in terms of gas laws: Boyle's law, Charles law and Gay-Lussac's law. Now for this discussion of absolute zero temperature, we have to go back to Charles law. Okay, now which states the relationship between volume and temperature of a gas at constant pressure. Now we are taking gas for the gas laws for a particular reason. You will see why. Because we are trying to analyze something which it will be by extrapolation. Okay, we have to go backwards, and for that we need to establish the relationship between volume and temperature at constant pressure. So we have volume, we have temperature, and pressure is constant. Okay, so as per Charles law, the mathematical statement is that if the pressure remains constant, then the volume of a given mass of a gas increases or decreases by 1 by 273.15 of its volume at 0 degree Celsius for each 1 degree Celsius rise or fall of temperature. This is the statement, and the mathematical equation is this. We have already discussed in gas law. So we have to basically take this equation, okay, V0, which is the volume at 0 degree Celsius, into 1 plus T by 273.15, where Vt is the volume at T degree Celsius at any particular temperature T degree Celsius. Okay, volume at T degree Celsius, and V0 is the volume at 0 degree Celsius. Okay, and T is the particular temperature T degree Celsius, okay, under question. So this is the important equation here. So we have a direct relationship between volume and temperature. This is in Kelvin. Why? Because 273 plus temperature in degree Celsius, that is equal to the temperature in Celsius. This is the relationship between Kelvin and Celsius scale. So volume is directly proportional to temperature at constant pressure. Okay, at constant pressure, volume is directly proportional to temperature for a given gas at constant pressure. So if we try to plot it, okay, if we try to plot it with temperature on the x-axis and volume on the y-axis, this will be the plot. Okay, as you can see, it is a straight line with a certain slope. It means volume is directly proportional to temperature. Now if you see, we in the top we have the temperature in Celsius, 0, 100, 200, 300 likewise, and below we have the equivalent temperature in Kelvin. I have deliberately shown both the temperatures in both the scales side by side. So here at 0 degree Celsius or 273 Kelvin, we have this line, which is the solid line, and after that we have the dotted line. This is the extrapolation. So if we take it backwards, extrapolate it backwards, this line will meet zero volume, okay, zero volume at minus 273.15 degrees Celsius. Okay, this is not minus 273 exactly, it is minus 273.15. okay, minus 273.15. okay, it will meet at minus 273.15 degrees Celsius. So here volume is directly proportional to temperature, that is the essence of Charles' law. Now for the temperature below 0 degrees Celsius, which we are talking, once we go to the left of 0 degrees Celsius, this will be the relationship between volume and temperature. V subscript minus T, the negative temperature, minus T degrees Celsius in Celsius, okay, not in Kelvin, below 0 degrees Celsius and minus T degrees Celsius. So that is equal to V0 into 1 minus T by 273.15. Okay, here it was for increase, here it is for decrease. So here if we see that the decrease of temperature, it results in the decrease of the volume of the gas, because volume is directly proportional to temperature. So if we take this line and extrapolate it backwards, the gas, it occupies zero volume at minus 273.15 degrees Celsius or 0 Kelvin, okay, or 0 Kelvin. So here we cannot take it any further backwards, okay, it is not possible to take it from here like this, it is not possible totally, because there is no such thing as negative volume of a gas. It is not possible, it is meaningless, okay, the volume of the gas, it cannot be negative. So we cannot take it beyond that, below that, okay, the volume of the gas, it cannot be negative. So this temperature minus 273.15 degrees Celsius or 0 Kelvin, according to kinetic theory of gases, all molecular motion, it stops at that temperature, okay, all molecular motion in a gas, it stops at minus 273.15 degrees Celsius or 0 Kelvin. All molecular motion stops, okay, all molecular motion, they stop at minus 273.15 degrees Celsius or 0 Kelvin. So the lowest possible temperature at which a gas which can have zero volume, zero pressure like that, at which the entire molecular motion stops, that is called as the absolute zero temperature, okay, the absolute zero temperature, minus 273.15 degrees Celsius or 0 Kelvin. And this is all done by establishing a relationship between volume and temperature through Charles' law, then plotting volume versus temperature graph in both Celsius and Kelvin scale side by side. We get a straight line with a certain slope, and then we extrapolate it backwards to achieve zero volume, and we note down the temperature at which it happens, that is minus 273.15 degrees Celsius or 0 Kelvin. And that is the special temperature, because according to kinetic theory, all molecular motion, it stops at minus 273.15 degrees Celsius or 0 Kelvin. And in practice, actually all gases, they condense to liquids and solids before even this temperature is reached, okay. So it is theoretically, practically, it is impossible even for the gases to reach that temperature. But still, for analytical purposes, okay, minus 273.15 degrees Celsius or 0 Kelvin, that is the absolute zero temperature. Okay. So here we'll discuss another important concept related to thermal properties of materials, and it is related to thermal expansion, actually volumetric expansion. So that is variation of density with temperature. Again, temperature comes into play here as we are discussing thermal expansion. So yes, supply of heat, increase of temperature, and variation of density because of thermal expansion. So as we all know, thermal expansion is the basic concept of increase in the size of a body when heat is supplied to it. Now it can happen in terms of three dimensions: linear, surface, and volumetric. Linear is one dimension, surface area is two dimension, volume is three dimension. Here we are talking about the volume expansion. So before that, just a quick recap of why thermal expansion happens. So we know that all objects, solid objects, they are made, every solid, liquid, gas, they are made of atoms and molecules, and they are held at equilibrium positions by interatomic forces of attraction. So when a solid is heated, the vibrations, they starts to increase, and as a result the separation between them, it increases, and as a result the material, it undergoes thermal expansion. This results in that. Now here we have to go for volume expansion. So let's say we have an object which has an initial volume Vi at initial temperature Ti. Heat is supplied to it. As a result, its temperature, it increased from, the temperature, it increased from Ti to Tf, and the volume, it increased from initial volume Vi to final volume Vf. This is the final temperature Tf, this is the final volume Vf. So here the change in temperature is delta T, which is equal to final minus initial, Tf minus Ti, and volume change is Vf minus Vi, final volume minus initial volume. Now here we have to establish a relationship between change in volume and change in temperature. So that is given by delta V, the change in volume, is directly proportional to the change in temperature, and the change in volume is directly proportional to the initial volume. When we combine these two, we get delta V is equal to gamma Vi delta T. Okay, this is the change in volume. Now the total volume, the final volume, that is equal to the initial volume plus the volumetric change. So Vi plus gamma Vi delta T. So if we take Vf here and Vi common here, we get Vi into 1 plus gamma delta T. And here the volume expansion coefficient, volumetric expansion coefficient gamma, which is the proportionality constant, that can be written as delta V by Vi delta T, and has the unit of degree Celsius inverse and Kelvin inverse. This is the coefficient of cubical or volume expansion gamma. Okay. Similarly, alpha beta, it is for linear and surface area expansion. We have already discussed that. So how density is affected with temperature? Now we know density is equal to mass by volume. Okay, density is equal to mass by volume. Now we know that mass cannot be altered, it cannot be changed, it is fixed. So if mass is fixed and volume is increasing, because thermal expansion lead to an increase in volume, volumetric expansion, so obviously density will decrease. So we have to establish a relationship between this variation of density with volume which is affected by temperature. Okay, so here we will write this equation: Vf is equal to Vi into 1 plus gamma delta T. Okay, Vf is equal to Vi into 1 plus gamma delta T. Now mass is constant. Now we know density is equal to mass by volume. So volume is equal to mass by density. Okay, this one, volume is equal to mass by density. Mass is fixed, constant. So here Vf is equal to m by rho f. Okay, rho f, that is the density at volume Vf. This is the density at volume Vf, that is the final density, and this Vi, that is equal to m by rho I, where rho I is the density at initial volume Vi, because mass is fixed, mass is constant. So we have substituted Vf with m by rho f, Vi with m by rho I. Mass is constant, it cannot be changed. And we have taken 1 plus gamma delta T common. So we have here, cancelling out mass on both LHS and RHS, we have 1 by rho f is equal to 1 by rho I into 1 plus gamma delta T. Okay, or rho f is equal to rho I by 1 plus gamma delta T, or we can write it as rho I into 1 plus gamma delta T to the power minus 1. We can write it as this. So we have rho f is equal to rho I into 1 plus gamma delta T to the power minus 1. So rho f is the final density. Okay, this is the final density of the material, and this is the initial density of the material. So applying binomial theorem here, we can write rho f is equal to rho I minus rho I into 1 minus gamma delta T. So obviously there is a decrease in the density. The final density is lesser than the initial density by this. Rho f is equal to rho I minus rho I gamma delta T, this. So there is a reduction in density with increase in volume through volumetric thermal expansion, because density is inversely proportional to volume. As volume will increase, density will decrease. As volume will decrease, density will increase. Mass is fixed. So this is the variation of density with temperature as a result of volumetric thermal expansion. Okay, so this is the relationship.